Hello everyone, this is Ratan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. Today's topic, we will see the derivation of energy equation from module 1. Okay, so what is energy equation? So basically, and when do we use that energy equation, and how it is derived, and what is the physical significance of energy equation, we will see in detail. So first, the principle of energy equation is, let's say, energy can neither be created nor destroyed. So it can be changed from one form to other form. So basically the conservation. So the conservation of energy, the meaning is, so we can change the one form of energy to other energy. Let's say we have mechanical energy. So that mechanical energy is converted to electrical energy. So for example, you can take dams. So where we generate the hydro power. So whatever the water that is coming from certain height, it is falling onto the turbine. So their potential energy is changing to the rotational energy of the turbines. So when the turbines are rotated, so that generate electrical energy, so it is stored. So here what is happening, so the water, whatever the energy that is consisting, the potential energy is converting to kinetic, then it is converting the mechanical to the electrical. So there are changes from one form to other form as the time progresses. So in this way, we can say that the energy is conserved and changing from one form to other form. So here it is neither created. So we are using actually. So we are just using the potential energy of the water which is falling from certain height, and that energy we are using, we are utilizing, and what we are doing, we are changing it to one form to other form. So that's the difference what we have. Now, so what we can do? So it can be changed from one form to other form, but it cannot be created, not destroyed. Actually, you cannot destroy the energy, or you cannot create a new energy. So whatever the natural energy resource that we are available, that thing we are actually utilizing and changing from one form to other form. Okay, so to do the derivation actually, so we will consider a matter which is, so consider a fixed amount of matter contained within closed boundary. So let us take, this is a some closed boundary. So what do you mean by open boundary? So open boundary is, let's say you have some so this is called open system. So where you have inlet, inflow and outflow, and this is called closed system. So closed system in the sense, what we have the flow of, let's say, flow of in and out as zero, but you have the interaction of energy, let's say energy in energy out can be done, work in or work out can be done. So these things are possible actually. Fine. So here what happens actually, so we are considering a closed boundary which is a fixed matter. So this fixed matter defines a system. So basically this is called a system. Fine. So system is an entity where you have some matter inside. So basically what is that matter? It can be water, it can be gas, or it can be some movable parts. So it depends actually. So it is an entity where it contains the matter. Fine. So let's say because of the molecules within, so let us consider a system. So where you have molecules and atoms where they are randomly moving with it. So each molecule or atom, it consists of certain energy. So when it changes, let's say you have atom A, you have atom B or C. So basically these A, B, C are, let's say, moving. So this is moving this way, this is moving this way, this is moving this way. So when they are moving randomly, so what happens actually? their interaction with the walls and the molecules and their energy changes will happen certainly. Fine. So these energy transactions or the energy movements, so whatever that happens will change the entire system energy. So let's say A has a temperature T, B has a temperature T1, C has a temperature T2. So when their collision happens, the average temperature T average so will change. So this is how there is a change in energy, let's say change in temperature. So basically, the energy per unit mass is called the internal energy. So here we have. So for simplicity, so let us consider a system with unit mass, so which is denoted by E. So the internal energy E is sum of the kinetic energy, potential energy, chemical energy, vibrational energy. So if you take this atom, so it consists of let's say it consists of potential energy, it consists of kinetic energy, it consists of mechanical energy, it consists of vibrational energy. Every like all the energies if we combine, so that energy we call it as the internal energy. Fine. Now, so let us consider a in the system. So let us consider a small particle or infinitesimal element. So whatever the heat that is applied to this element is delta Q, and whatever the work that is done on this element is delta V. So whatever the change that is coming in the entire system is dE. So here basically whatever the first here the region outside the system defines its surroundings. So whatever the boundary we have drawn, so that boundary is an enclosure to the system. Fine. So what is system? System is an entity where you have matter embedded in it, or you have a matter which is here, which is present here. It is enclosed in it. Now outside to the system, we call these things as surrounding. So when we say this as surrounding, so that surrounding has a negligible, let's say a negligible effect when you have very far away from it. So let's say you have a temperature T is equal to some 10,000 degrees Celsius. So here, if you have let's say effect coming here, let's say 3000, somewhere here it is 2000, somewhere it is coming as 298. So whatever the free stream zone is there, it is called unaffected zone. Whatever the zone that is affected, that is called surroundings. So surroundings area can be specified specifically only when you have the effective nature from the system. So if you have the effects from the system to the nearby places, then that particular entity is called surrounding. If not, we does not call it as surrounding. Okay. So let an increment amount of heat is added. Let's say this is delta Q. So this is delta Q by the system from the surroundings. So from the surrounding, we have a heat higher than the system. Therefore, a heat is applied to the system, which is of delta Q. Also, there is a work done on the system by the surrounding, so which is given by delta W. Okay, so both heat and work. So here you can see both heat and work are basically are forms of energy where so we say that work is done on the system and heat is added to the system, and when there is a interaction between work and heat, so there is a change in energy of the system. How? So let us consider this system itself again. So here you have particles. Let's say this is A and B and C. So when you apply the energy to A, let's say less energy to B and medium amount of energy to, so let's say this is C, B. So TA, TB, TC. So what happens actually, we are applying some heat at point A, B, C. So once when a particle or a molecule gets heated up, what happens? The energy changes. Fine. So the energy is changing such a way that they occupy the thermal energy, and they move randomly from one point to other point clearly actually. Fine. So what happens actually? So they possess the kinetic energy, they possess potential energy, they possess mechanical energy, and they possess vibrational energy. So these energies they will possess actually. Okay. And when we apply the heat, they will change. And when we do work on the particles, they will also change again. So these changes, whatever happens, so at point A, B, C, they are taken average. Let's say T average at A plus T average at B plus T average at C is equal to total T average of system. This is what we get. Fine. So this is what happens, and this is what we get when we take different points in the system A, B, C, and when we add up to them, so then we get the average. So then whenever we get these type of changes, what happens actually? There is a change in energy, internal energy of the system. How? Initially, let's say we have KE1, comma PE1, comma ME1, comma V1. Let's say these are the initial energies constituting E1. So when you combine these things, we get internal energy of system E1. So when you apply heat and when you apply work on the system, so what happens actually? They will change to E2. So what is the meaning of E2? So you will have a new KE2, PE2 plus ME2 plus V2. So these things will happen actually. Fine. So therefore, what happens? So whatever the changes that happen from one state to other state, E1 to E2, so this is happening because of Q, heat and work. So because of heat and work, the state of system is changing from E1 to E2. Fine. So what happens actually? When added to the system, they change amount of internal energy system. So basically, the internal energy is changing from where E1 to E2. So that is denoted by dE. So dE is nothing but difference between E1 to E2. Okay. So basically, this is coming from the first law of thermodynamics. So first law of thermodynamics says that, so when you apply some amount, when there is an interaction of heat and work on the system, so there is a change in internal energy of the system. Fine. So when we have the change in internal energy of the system, so what happens actually? The variables Ke1, Pe1, Me1, V1 changes, and whatever the matter contained in it, P1, P2, P3. So let's say the values will change. All the values will change when you have change in the energies. So first law of thermodynamics basically deals with the energy and interaction. So where when we apply some amount of heat and work to the system, there is a change in internal energy of the system. So this is of conservation. This is basically a form of conservation of energy. Now, so for the derivation, let's say we take B1. So B1 is nothing but the rate of heat added to the fluid inside the control volume from the surroundings. So again, let us take this as a control volume. So already in the previous sessions or in the modules we have seen. So what do you mean by control volume? So basically control volume is nothing but an imaginary volume. It can be of any shape. So no need to be of a square, circle or any other shape. So this is called a control volume. So where you have the interactions, so between the system This is system and this is surroundings. Okay, so when you have this interaction, okay, so the system and surroundings between, let's say, now what happens, there is a amount of delta q which is applied on the system. So here this is called b1. So what is b1 actually? It is a rate of heat added to the fluid inside the control volume from the surrounding. So this is surrounding. From the surrounding, we are applying heat delta Q, so to the system. Fine. Next, we have B2. So what is B2? B2 is called rate of work done on the fluid inside the control volume. So here we are having an additional entity, so which is called delta W. So delta W is nothing but the rate of work done inside the control volume. So here we are doing some work inside the control volume. So that one, so we are mentioning it as B2. Fine. So this one is called B1. This one is called B2, and B3 is nothing but a rate of change of energy of the fluid as it flows through control volume. So example, what we have, so we have, let's say, let us take an engine. Okay, so in the engine you have, let's say, compressor. So here you have compressor blades. So here you have compressor blades. So through this, the flow is going, let's say. So here you have heat appliement, let's say delta Q. So here you have work actually. Fine. So flow out. Fine. So this is flow in. Now what is happening? Let's say when a flow is entering through the system, basically this open system. When flow is entering, what happens? Because of compressor, there is a work applied on the flow. Then there is a heat applied on the flow. Because of change in work and heat, there is a change in internal energy of the flow, which is going outside. So basically, what is happening? You take any matter or any entity, when we apply the heat, when we apply the work to the systems. So what happens actually, or the entity, delta Q, the change in heat, delta W, the change in work, will contribute to change in internal energy, which is B3. So here we have, so B1 plus B2 is equal to B3. B3 is nothing but rate of change of energy of fluid as it flows through the control valve. Fine. This is what we have. Now, so first consider rate of heat transferred to or from the system. So basically, we have a entity called volumetric heating. So surface is there, volumetric heating is there. So when we transfer the energy or the heat to the system, so you have the volumetric heating. So volumetric heating in the sense what? So if you take this system, so throughout the entire volume, so it is getting heated up actually. Fine. So this one we can take it as QdV. QdV is nothing but, so entire place. So the heat is actually dissipated or absorbed throughout the volume. So dV is nothing but the volume of the control volume. So here we have volumetric heating of the fluid inside the control volume due to absorption of radiation originating outside the system or local emission of the radiation by the fluid itself. Okay, if the temperature of inside control volume is high enough. Fine. So what we are doing first, we are considering the heat transferred to or from the fluid. Okay, so when it is happening, so you have the volumetric heating in the sense, so throughout the volume, the flow or the system will get heated up. So this happens to be because of the absorption of radiation which is coming from the outside. Okay, and where the control volume can hold the temperature within it. Fine. So in addition, there may be chemical combustion process. So the volumetric heating can happen in two ways. One, it's like if you have any radiation or anything that is happening and that poses on the system, that is one thing. The other thing what we have is the radiation which is coming out, that thing we have. The other one is chemical combustion process which is taking place inside the volume, as I told you. So when you take an let's say engine, so let me draw the diagram. So here you have compressor, here you have heat, here you have turbine. Fine. So when flow is going inside, here there is a work, here there is a Q, here there is a work out or extraction and heat out. Okay. So what is happening actually? So when you take an engine, so the any engine you take, turbojet, turbofan, turboprop, turboshaft, ramjet, scramjet, any engine you take. So whatever the air that is going from the static atmosphere or the free stream, so will enter to the inlet. So when it is entering to the inlet, what happens? There is a change in pressure, there is a change in temperature, there is a change in velocity. So when the thermodynamic variables, what are thermodynamic variables? P1, let's say T1, rho1, V1, let's say E1. When they change from one point to other point, the meaning is the state has changed. So the thermodynamic changes where it is happening from station 1 to 3. So P1 is changed to P2 and T2, row P1 to P2, T1 to T2. So P1 to P2, T1 to T2, row 1 to row 2, V1 to V2, E1 to E2. So when it is changing, so when it is station 1, this is station 2, this is station 3, station 4. What happens? At station 1, you have P1, T1, row 1, V1, E1. So at station 2, it will become P2, T2, row 2, V2, E2. Why? When there is a change in what you say, the flow interaction with the system, then the system properties will change. Now, when we actually compressing the air by means of compressor, P2 will be high, T2 will be high, the rho 2 will be high, velocity will become low, and internal energy will increase. So that is what happens. When it is going from station 2 to 3, then again the pressure changes. P2 to P3, T2 to T3, rho 2 to rho 3, V2 to V3, E2 to E3. Okay. So at this point, you will have P3, T3, row 3, so on. Fine. And similarly, at 4, it will change P3 to P4, T3 to T4, row 3 to row 4, next V3 to V4 and E3. So here what is happening at each and every stage, so there is a change in temperature, there is a change in work interaction, therefore there is a change in internal energy of the system. So this tracking phenomena has to be done throughout the process. Now when there is a heat applied, that heat can be coming from two ways. One is radiation absorbed from the external atmosphere, from the local thing, or it is emitted from the system, that is one thing, or due to the chemical process or the combustion process that is taking place inside the engine. Fine. So that is getting heated up. This is one of the possible. Now what happened? So in addition, if the flow is viscous, so if the flow is viscous, what happened? So what is viscosity actually? Viscosity is a resistive force which is offered by the fluid medium. So you take any fluid, you take viscous, like let's say Newtonian fluid, non-Newtonian fluid. Newtonian fluid is nothing but where tau is proportional to mu into dou u by dou y. So you have a linear relationship between shear stress and shear strain. Okay, for applied stress, okay, the applied strain, like the strain is coming actually. Fine. So that is called Newtonian fluid. When you take non-Newtonian fluid, even for the non-Newtonian fluid, so the linear relationship will not hold, and you have a like exponential, like say power n plus 1, some other relationship will be there. So if n is equal to 1, then you have this as Newtonian. So if n is greater than 1, or let's say less than 1, or some relation if it has, then it is called non-Newtonian fluid. So when there is a interaction between two different flows, okay, the two different flow interactions will happen, and those interactions will cause a viscous effect. So you have a fluid layer V1, you have fluid layer V2. So when these two interactions will happen, what happens actually, the because of change in velocity nature, you have the rotational effect, you have the resistive force which is offered by V1 on V2 and V2 on V1. So this is interaction between two fluid layers. But if you take any wall, and when a flow is going, because of cohesive and adhesive natures of the fluid between the solid and molecules, between the fluid molecule and solid molecules, so there you have viscosity effects. Even this viscosity effect, the shear stress, can add or can transfer the heat to the control volume by means of thermal conduction, mass diffusion across the control surface. So previously what we have seen, so here we have seen the radiation, or let's say the temperature which is evolved from the system, or temperature which is observed to the system, or heat addition which is coming from the combustion chamber. So these things are happening. But here what is happening here, the viscosity effect, the flow viscosity is making the heat transferred to the control volume by means of conduction or mass diffusion. So this viscosity effect, what is viscosity effect? When there is a change in we have a flow, that flow is getting interacted with the surface. When these two interaction will happen, because of the adhesive cohesive nature, there is a change in temperature, there is a change in what do you say, pressure or velocity, and this will actually take place with the help of conduction. So conduction is nothing but how, so you have a, let's say, a hot plate, you have a cold flow which is going. So boundary layer, the viscosity effect, what happens? The first layer will stick to the hot. So because of the sticking nature, the conduction will happen between the fluid molecule and solid molecule. So therefore, the cooling will take place. So what happens actually? Because of the viscous effect, the change in temperature is happening because of thermal conduction. Fine. So combustion, in addition, like you have combustion which is taking place. So therefore, this volumetric heating, so basically Q dot, this Q dot is nothing but the volumetric heating which is happening inside the control volume. So rho is nothing but the density. So dV is nothing but throughout the volume. So the rate of volumetric heating, you can see it has triple integral. So triple integral in the sense throughout the volume. So Q dot, which is happening volumetric heating inside the volume, rho density, dV is throughout the volume. So therefore the B1 is nothing but, so this is the volumetric heating which is coming, and other one Q dot viscous is nothing but the heat which is coming through the viscous heat. Fine. So this is B1. Fine. Next we have B2. So work. We have completed about the heat. Now we will see about work. So the rate of doing work on moving fluid, F dot V. So whenever you have a work, whenever a fluid is moving, So the rate of work done because of moving fluid is F dot force into velocity. This F force of different, you have body force, you have surface force. So the F force is divided into two. One is body force, other one is surface force. So in the body force, you have the work done due to uh, gravitational force, electromagnetic force, other forces actually, gravity or other aspects. That is called the body force throughout the volume. Surface forces, here you have pressure and shear. Now previously, what we have seen the shear stress or the viscosity is contributing to heat. Similarly, the shear stress and viscosity can contribute to the work also, and the pressure can contribute to the work also. So that is why you can see that. So here, work done due to pressure we have, fine, and work done due to viscosity, fine. So here we have work done due to pressure, so which is coming from the surface force, and work done from the viscous, which is coming from the shear force. And this is what the volumetric work, which is coming from the body force, fine. So here you can see the rate of work done on the fluid inside the control volume V due to pressure is, so the negative is because like you have a change in the direction of the opposite. So let's say the pressure is acting in this direction, the velocity direction may be different, or let's say this is because of changing the vector magnitude, fine. That is one thing. And next, the volumetric heating of work, or the rate of work done on inside volume because of body force, as I told you. So force F is divided into body force and surface force. So here you can see surface force, you have pressure and viscous, and body force you can see you have the rate of work done on the fluid inside volume V. Here we have this one, fine. So triple integral of rho F dV V. This is what we have, and the net rate of flow across the control surface. So this is what we have. So here this is B2, fine. So basically, what is B1? B1 is nothing but the rate of change of heat applied to the system, or heat that is coming from out of the system. Next, B2 is nothing but rate of work done on the system or work coming out from the system. And B3, here the net rate of flow of total energy across the control surface. So what is the net rate of flow across the control energy? So here E is internal energy. So V square by 2 is nothing but, sorry. So this is PE, and V square by 2 is nothing but your kinetic energy. So this is throughout the surface. Fine. Now, so here you can see the time rate of change of total internal energy due to transit variations in flow rate. So when it happens, so when there is an interaction between the work and when you have interaction between the heat between the system, then you have this time rate of change of total energy inside the control volume. Now, as I told you, when you have a system, so here you have, let's say, molecule A, B, and C. So when a heat is applied, delta Q, when a work is applied, delta W, so what happens? The internal energy EA, EB, EC will change. Initially, they have common energy, let's say at every point EA, EB, EC may be equal. But when there is an interaction of work and the interaction of heat to the system, what happens? EA is not equal to EB is not equal to EC, because EA may have high amount of kinetic energy, low potential energy. EC may have high amount of potential energy and low end of kinetic energy. EB may have different. Fine. So what we do is like we do average. Fine. When there is a applied amount of heat and work is happening in the system, so what happens? There is a time rate of change of total energy of the system. So here change in energy of entire system that happens. Fine. So if you see throughout the volume, so you actually, this is for one specific entity. So if you take E plus V square by 2, so that is for only one single atom or one specific quantity. So when we want to track with respect to time, we are applying this dou by dou t. So dou by dou t is nothing but here you have time rate. The time rate of change is nothing but dou by dou t. So inside the volume is coming from the volume integral. Fine. So total energy is nothing but E plus V square by 2, which is happening. So if we want to track, so whatever the total energy that is coming inside the volume is this one. So the first term, you can see whatever the variations dou by dou t rho E plus V square by 2 dV. So this thing is coming because of variation that is happening inside the control volume, and rho V dot ds and E plus V square by 2. So that change in energy that is happening over the surface. Fine. So here what we have, so this entity is coming from B1. So what is B1 here? So B1 is nothing but whatever the heat that is applied to the system, either from the surroundings because of radiation or heat emitted from the system. So which is combination of viscous and volumetric heating. Fine. And this is for B1. Next, what is B2? So this is happen to be B2. So what is B2 we have seen? So B2 is nothing but when there is a motion of the fluid particle, so the work is done, and the work is done because of body force and surface force, and the body force is because of the gravitational force or electromagnetic force. The work is done because of the gravitational pull or electromagnetic force on the particle. Next, surface force is nothing but the pressure and the shear. So that's why here you have the work done due to pressure force and work done due to viscous force, and this is volumetric heating. This is B2. So this is what we are doing. So B1 plus B2 we have done. Next is equal to B3. So what is B3? So the change in internal energy that is happening throughout the volume. So the rate of, or the time rate of change of total energy that is happening inside the volume due to change in flow variables. So when the temperature, when the pressure, when the density and the velocity, if every other things are, if all the things are changing, then the total energy also will change. Fine. So therefore, what happens actually when the total energy is changing? Let's say we have time from T1. So when we applied initially a temperature at time T1, so let's take this. Let's take in this way. At T1, we have P1, rho 1. Next T1 temperature, V1. So these things here. At T2, so when you have as the time progresses, when the flow variables change, P2, rho 2, T2, V2. So when these variables are changing from T1, P1, rho 1, T1, V1 is there. From T2, P2, rho 2, T2, V2 is there. When they are changing, what happens? This time rate of change is making the total energy change. So even the flow variable of P1 is changing to P2, rho 1 is changing to rho 2, T1 is changing to T2, V1 is changing to V2. What happens? It is making the entirely the system changes actually. So entirely the flow variables are changing, and entirely the system properties are changing, and entirely the system energy is changing. So that is what we have this term dou by dou t of triple integral rho E plus V square by 2 into dV. Next, so whatever the change in system we have on the surface due to work done. Okay, so this is B3. Therefore, B1 plus B2 is equal to B3. So this is the total energy equation derivation which is coming from the first law of thermodynamics. Okay, so here what we have seen, here we have seen three things. One is the heat energy, other one is the work, other one is the internal energy. So when there is a change in heat and work applied to the system, then there is a change in internal energy. So the possible ways what we have seen is the heat coming from the surrounding or heat going from the system, that is one thing, and heat coming to the viscous effect, that is one thing which is added to the B1. Next, the work done on the system or work done by the system. So the work is coming in two ways. One is coming from body force and surface force. Body force is nothing but gravity and electromagnetic. Surface force is nothing but the pressure and the viscous. And the third thing, B3, when these two, when B1 and B2 are interacting to the system, then the B3, whatever the change that is coming, that changes the throughout system property, the total energy inside the control volume, which happens to be dou rho by dou t, volume integral rho into E plus V square by 2 dV, plus this is of surface entity. Fine. So with this, we have seen the derivation of conservation of energy equation, where we have seen the transformation of energy, heat energy and work energy, like work and heat from one phase to other phase. When you have the interaction of work and heat, then there is a change in internal energy. With this, we conclude this topic. In the next module, we'll see the other topics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.